let's go through the main objective of this task for question 2. There are 4 core goals we wanted to achieve with this program. First, understand and implement a dynamic timing delay loop in ARM v7 assembly using nested loop structures or variable counter registers. Second, analyze the relationship between the processor simulated execution cycles and real-time physical delays, which is 1 second, 0.5 second, and 0.1 second. Next, program a state sequence that automatically shifts execution speeds across 3 distinct cycles using a single trigger. And lastly, optimize code structure by using a reusable subroutine BL to eliminate code duplication.
So now, let's look at the expected result. When we first load and run the code, you will notice that all 10 red LEDs are completely dark. At this stage, the processor is sitting in a polling loop, waiting specifically for the activation of switch 4. No other switches will trigger the sequence. When I flip the switch 4 up for the first time, the running light sequence begins. You can see the LED lighting up one by one from right to left. The movement is steady and slow because the program has loaded the 1 second delay interval once the light passes the final LED. The sequence stops and the program waits for me to flip the switch back down to register the next state. And then, on my second press of switch 4, the internal state tracker advances. Now, notice the speed. The LED are running across the board twice as fast as before. The delay has been cut in half to exactly 0.5 seconds. Again, the system resets once the light reaches the end. For the third press, we enter the fast mode. This uses our shortest delay of 0.1 second. The LEDs sprint across the row almost instantly, demonstrating the program ability to handle rapid timing interval. Finally, what happens if I press the switch for the fourth time? As you can see, our reset logic kicks in, the state tracker overflow and return to 0. And the cycle starts all over again with the original 1 second slow speed. This confirms that our state machine and delay loops are working perfectly in sync with the hardware switches. So next, let's start with the system logic. As you can see in this flowchart, the program acts a simple state machine. First, initialize. When the system boot up, it's clear all the LEDs and set our state tracker register to 0. Next, polling for input. The program enters a loop where it continuously checks the status of the switches. It isolates switch 4, completely ignore all other inputs. Next, state selection. Once switch 4 is flipped, the code reads our state counter. Depending on whether the count is 0, 1 or 2, it branches to select a specific timing delay. Next is the animation loop. It then calls the run light subroutine. This turns on the first LED, counts down a delay loop, shift the bit to the left to turn on the next LED, and repeat until all 10 LEDs have flashed. Next one is state update and release. After the animation complete, the state tracker increment by 1 so it's ready for the next speed. Crucially, the program hits a wait for release block. It freezes here until you physically turn switch 4 back off, preventing the fast processor from accidentally skipping through multiple modes at once.
Next, let's dive into the discussion for question 2, where we analyze the core technical mechanics of our implementation. We have broken this analysis down into 3 main areas: memory addresses, input isolation, and data manipulation. First, under addresses, our program targets specific memory map input-output location on the DE1 SoC board to interact directly with the hardware peripherals. We use the hexadecimal address 0 times FF to 00000 to write data out to turn the red LEDs on and off, and we query address 0 times FF to 000040 to read the current physical states of the slider switches. Second, for isolating switch 4 to ensure our system exclusively reacts to our target trigger, the code applies a precise binary filter using the test instruction, which is tstr3, and hashtag 0 times 10, because hashtag 0 times 10 corresponds to bit 4 in binary. This masking operation acts as a shield. It ensures the processor only process command when switch 4 is flipped, meaning flipping any other switch on the board does absolutely nothing. Third, for bit shifting using LSL, instead of writing tedious, repetitive lines of manual code for every single individual LED state, our program utilizes logical shift left or LSL. We start by loading a basic binary 1 into our register to light up LED R0. From there, the program dynamically slides that bit to the left step by step. This clean arithmetic approach scales up through the registers automatically to light up the next sequence of LEDs.
Okay, for this discussion part, I will explain three another more important part from the program: the limit OS400, the brain of the program, and the release check. Okay, first, the limit is OS400. In the LED sequence, the program starts from LED R0 using the value OS01. Then the instruction LSL R5 R5 shift the value to the left one by one. This makes the LED move from the LED R0 to LED R1, then LED R2, and continues until LED R9. After LED R9, the next shift becomes 0x400. So, 0x400 is not actually one of the LEDs that we want to display. It is used as the mathematical boundary to tell the program that the sequence has already passed LED R9. When the program detects this value, it stops the loop and turns off all LEDs. Okay, second is the brain of the program, is register R8. Register R8 acts as the state counter. It stores the current mode of the program. For example, when R8 is 0, the LED runs with the slowest delay, around 1 seconds. When R8 becomes 1, the delay changes to around 0.5 seconds. When R8 becomes 2, the delay becomes faster, around 0.1 seconds. After each press of switch 4, the value of R8 increases by 1. But since the program only has 3 modes, once R8 reaches 3, it will reset back to 0. This is how the program cycles through the 3 speed modes repeatedly. Okay, the third is the release check. This is very important because the processor runs very fast. If you do not include the release check, if you do not include the release checks, one single long press on switch 4 may be detected as many presses. This can cause the program to skip from mode 1 to mode 2 and mode 3 instantly. To avoid that problem, the program waits until the user turns switch 4 off before accepting the next input. So, one press will only count as one mode change. This makes the program more stable and easier to control. So, overall, the limit 0x400 controls when the LED sequence stops. Register R8 remember the current speed mode, and the release check prevents unwanted multiple input from one switch press. That's all for discussion, and let's look for the table.
So now, let's look at how the processor actually interpret our hardware inputs and outputs at a binary level. So the first one is switch inputs and hex masking. If you look at the top diagram, we have our 10 slide switches labeled S9 down to S0. To isolate switch 4, we apply a software mask by setting bit 4 to a logic height 1 and all other bits to 0. We get the binary pattern is 0000010000. In hexadecimal, this translates to 0x010. This is the exact mask our assembly code used with the TST instruction to ensure the program only responds when switch 4 is flipped. So, the first condition, the first press, 1 second delay. When switch 4 is toggled on, its data register shows a 1 at position S4. The running light routine is called. It starts at the rightmost LED L0, turning it on with a logic 1. The program executes a logical shift left one time every 1 second, causing that active hype bit to slide smoothly from right to left across the LED bar. So when we turn the switch off and flip it on a second time, we look at condition 2. The input and starting output layout look identical, but the internal timing changes. This time, the program triggers the bit shift at a faster pace once every 0.5 seconds. Moving to condition 3, on our third press, the exact same binary pattern is initiated but the bit shifting frequency is maximized, advancing the hype bit every 0.1 second for a rapid effect. Finally, let's look at the default condition at the bottom. When switch 4 is turned off, its register value drops back to 0. Consequently, all output register from L9 down to L0 receive a logic 0. This cuts power to the entire LED block, instantly clearing the display and resetting our system back to its baseline idle state. This clear hardware data mapping explains exactly how shifting simple binary 1 second and 0 seconds creates our dynamic running light animation. For next, let's talk about the coding. At the top of the code, we define our memory map, input and output addresses. 0xFF200000 for the LEDs and 0xFF200040 for the slide switches, right under our entry point. We clear all LEDs to 0 and initialize register R8 to 0. This R8 register is crucial because it acts as our internal state tracker to remember how many times the switch has been pressed. In the next blocks, the program constantly reads the switch value into register R3. The instruction is tstr3 hashtag 0x10 applies a binary mask to check only bit 4. If switch 4 is not pressed, the BEQ instruction keep looping right there, ignoring all other switches. Next is once switch 4 goes high, the program moves to the state verification block. It uses comparison to see what is stored in our tracker R8. If R8 is 0, it loads a large counter value of 20 million into R4 for the 1 second delay. If R8 is 1, it loads 10 million into R4 for the 0.5 second delay. If R8 is 2, it falls through and loads 2 million into R4 for the rapid 0.1 second delay. Once the appropriate delay value is loaded into R4, the program branch to run the LED sequence, increment the tracker, and waits for the switch to be released before restarting the loop.
For the second part of the code, it starts with the label run_sequence. At this point, the program already knows which delay speed to use based on the current state. The instruction bl_run_light is used to call the subroutine name run_light. This means the running LED sequence will start and the delay value stored in R4 will control how fast the LED move. After the LED animation finish, the program goes to update_state. Here, the instruction add R8 R8 #1 increase the state tracker by 1. This allow the next switch press to use the next speed mode. For example, the first press use around 1 second delay, the second press use around 0.5 second delay, and the third press use around 0.1 second delay. Then, the code compare R8 with the value 3. Since we only have 3 states, which are 0, 1, and 2, if the state become 3 or more, the instruction move GER8 #0 will reset it back to state 0. This makes the speed cycle repeat again from the beginning. And next, the program enter wait_release. This part waits until the user turns switch 4 off. The reasons for this is to prevent the program from changing modes too quickly while the switch is still on. The program keeps checking switch 4, and if switch 4 is still on, it stays in this loop. Okay, and then once switch 4 is released, The program branched back to wait underscore press, meaning it is ready to wait for the next switch press. After that, the code enter the subroutine run underscore light. The subroutine control the LED running animation from LED R0 to LED R9. The instruction push R5, R6, R7, LR save the register so that the main program will not be affected. Then move R5 #1 set the first LED position, which is LED R0. The LED base drive is loaded into R6. And then the inside light loop, the instruction store R5, R6 turn on the current LED. Then the delay value from R4 is copied into R7. The delay loop repeatedly subtract the delay loop repeatedly subtract 1 from R7 until it becomes 0. This creates the time delay before moving to the next LED. After the delay is finished, LSL R5 R5 #1 shift the LED position to the left. This moves the light from one LED to the next LED. The program compare R5 with 0 at 0 which means it check whether the sequence has passed LED R9. If it has not reached the end, it repeats the loop. Finally, when all LED have been shown, the code sets R5 to 0 and store it to the LED address. So all LEDs are turned off cleanly. The instruction pop R5, R6, R7 PC restore the save, register and return to the main program.
In this video, I am going to demonstrate the live simulation of our solution for question 2 using CPU ladder. The objective of this task is to manually cycle through 3 distinct running light speeds, which is 1 second, 0.5 second and 0.1 second by pressing switch 4 for each individual speed cycle. Our code uses an internal state register to track how many times the switches has been pressed. To begin, I will move my cursor up to the top menu and click the compile and load button to assemble our program. As you can see in the message window at the bottom, the build is successful with 0 errors. Now, to start executing the code, I will click the continue as a run button. The program is now actively running in the background. Currently, the CPU is in a polling loop waiting for the first switch trigger. The LEDs are off because our state counter starts at 0. Now, watch the switches and LEDs panel on the right as interact with switch 4. I will toggle switch 4 on and off for the first time. So this activates our first cycle. If you watch the red LEDs panel, the light moves from LED R0 across to LED R9 at a steady pace. This is our 1 second delay speed. Once it hits the end, the LEDs turn off and the program waits for the next input. So now I will toggle switch 4 on and off again for the second time. This increments our internal counter and triggers the second cycle. Notice how the light is now scanning across the panel twice as fast. This represents our mid-tier 0.5 second delay speed. Finally, I will toggle switch 4 on and off for the third time. This triggers our third cycle. The light zooms through all 10 LEDs almost instantly, demonstrating our high speed 0.1 second delay. If I were to press the switch a fourth time, the counter will automatically reset back to 0, allowing the entire sequence to start over. This successfully demonstrates how state counter can control dynamic processor timing in ARM assembly. That concludes my simulation demo for question 2.
Okay, for the conclusion, this lab successfully demonstrates state control running light application using ARM v7 of the DM1 SoC simulator. From this program, we use memory map input and output. The input comes from switch SW4 and the output is shown on the red LED from LED R0 until LED R9. When the user turns on switch 4, the program reads the switch condition and start the running light sequence. The LED will light up one by one, moving from the first LED until the last LED. This program also uses register R8 as the internal state tracker. The purpose of the state tracker is to control the speed of running light, which is press of SW4. the program changed to the next delay mode. There are 3 delay modes used in this program, which are around 1.0 seconds, 0.5 seconds, and 0.1 seconds. After the third mode, the state will reset back to the first mode so the speed cycle can repeat again. Another important part is the release loop. The release loop makes sure that the program only changes one state for one physical switch press. This prevents the processor from reading one long press as many repeated presses. And lastly, this program uses logical bit shifting to move the LED pattern. Instead of writing each LED value one by one manually, the program shifts the value to the left. This makes the code shorter, cleaner, and more efficient. So overall, this lab helps us understand how to use switch input, LED output, delay loops, state tracking, and bit shifting in ARM v7 assembly programming. And that's all for us. Thank you.